So row total times column total divided by the grand total. And then the p-value. So when H naught is true, remember our null is that they're independent. When that is true, and the assumptions for the chi-squared test are satisfied, then x squared has approximately a chi-squared distribution with the rows minus 1 times the number of columns minus 1 degrees of freedom. The p-value associated with the computed test statistic value is the area to the right of chi-squared under our appropriate chi-square curve. Well, again, this should all sound familiar from yesterday. Anyone want to take a stab at what that first assumption will be? They're from a random sample. That's right. So the observed counts are based on data from a random sample. That's our first assumption. And then the second assumption is that all expected cell counts have to be at least 5. If counts are less than 5, then we're going to have to either combine rows or columns until we get the counts up. So let's look at our first of 2 examples that we're going to do today. It's called the body art example. Right? A paper called the Contemporary College Students and Body Piercings article described a survey of 490 undergraduate students. Now, if you look in your notes, there's a typo. I think it says they described a survey of 450. It's actually 490. So in your notes, you may want to correct that typo. What's that? Yeah, and the example, the body art example, second line, it says describes the survey of, I think y'all says 450. That needs to be 490. 490 undergraduate students at a state university in the southwestern region of the U.S. Each student in the sample was classified according to class standing, meaning freshman, sophomore, junior, or senior, and body art category. So do they only have body piercings? Do they have only tattoos? both tattoos and body piercings, or no body art? Is there evidence that there is an association between class standing and response to the body art question? Okay, so what tells us in this problem, other than me telling y'all, that we have to test for independence here? If you read the problem, what would tell you that we're testing for independence? That's right. So when you read a problem and it says that there is an association between, that is telling you to test for independence. That's what that's telling you. Okay, so first, let's get our hypotheses. What would the null hypothesis be? What would our null be? Well, we're testing for independence. Yep, so that we could say that class standing and body art category are independent. That would be the null. Class standing and body art category are independent. Which means the alternative would be class standing and body art are not independent. That's what those say right there. Class standing and body art are independent and then are not independent. Okay, so now, once we've done that, we need to look at the expected counts. So we gotta get the expected counts, which means, for one, we need to get column and row totals. Let's get the column totals first. So what would our total be for the body piercings only column? $145. What about the tattoos only column? Should be 44. Okay. What about both body piercings and tattoos. 54, that's right. And then no body art. $247. So there's our column totals. Now we need to get row totals. So how many freshmen did they survey? You're 68. And what about sophomores? $128. Juniors? And last but not least for totals, actually it's not the last one, it's second to last. Seniors. $115. So then we can add either the rows or the columns, it doesn't matter, we should get the same value. Add them up to get our grand total. What was that, Will? It should be 412. Should be 490. Did you figure out what happened? Yes. Okay, perfect. Okay, so we got our totals, but that's really only the beginning of the game. The main reason we got the totals was so we could get the expected counts. Yes. So for the expected counts, we have to do row times column divided by grand total for each cell. For instance, for the freshman, body piercings only, you would have to do 168 times 145 divided by 490. What would that get us? And we can do just one decimal place. 49.7, that's right. And so instead of having us calculate all 16 of these, since you'll have plenty of those to calculate on your assignment, we calculated one. On the last example, there's only 6 we'll have to calculate, so we'll do that one in its entirety. But for this one, if you were to go through the process, the expected counts would be in parentheses. Now, let me just put in a little word on expected counts. It is part of the assumptions that we say they're greater than 5. You must show me the counts in order to say they're all greater than 5. You can't just say, yes, they're greater than 5. Okay, great, what are they? I mean, if that's the case, I could stand here and say, the sky is pink. Really? Show me. No, the sky's pink, just believe me. So assumptions, we've got to prove it. So I'll give y'all a second to get the assumptions written down. If you've already got the assumptions written down, start trying to calculate the test statistic. Or not the assumptions, the counts. Okay, so there's not really a spot on your notes. I didn't catch this until last period. But there's not a spot on the notes for this example where we talk about assumptions. But we need to state them before we can continue. So first, I guess we'll just do them down here. You can do them at the bottom of the page, the top of the next page, wherever you want to do them. Assumptions. Are they random? Are they randomly selected? Then tell us that. Yeah, tell us they are. For the purpose of this example, we'll assume so. For the purpose of the example, because if they weren't random, then this wouldn't be much of an example.
what happened, the example, but really, it's not random.
If it states that they are not randomly selected, then we would not be able to run a hypothesis test about the populations. Yeah.
I don't think we're gonna look at a problem like that.
Yeah. I wouldn't give y'all one like that because it has, in order to run any kind of statistical test, it's got to be random. Or any test that I've taught y'all, it has to be random. There are certain higher level tests that deal with data that is not randomly compiled, but I can't, off the top of my head, I can't remember.
It's not random, so that's a problem.
Bonus, maybe? Put it in like 8-point font. This data is not randomly selected.
Yeah.
Or say the data is in an 8-point font, not randomly selected. Okay, so that assumption is met. We're going to say it is at least. Now the second assumption, are all of our expected counts 5 or more? Yes. Now I'm kind of writing these backwards because I don't have room to write down here. So 2, we can say all expected counts. Are greater than or equal to 5. Yes. So what I would do is just reproduce the table on your assignment, and then do like we did here in parentheses, just put your expected counts. Yeah. Okay, so how many degrees of freedom would this data have? It would be 9, yes. We have 4 columns, 4 rows. So you do 3 times 3, because we have to eliminate one of each. 3 times 3 is 9. This has 9 degrees of freedom. And then next, we have to actually calculate stuff. So for the test statistic, how would I write that first one? That's right. And then we would keep going and do all 16 of them and end up with 29.48 as your chi-squared value. Now, here's something else I saw on the 12.1 homework as I was grading it. Since I assigned all odd problems, people would work it out. And then this piece would be wrong, but then they mysteriously got the right answer. So what do y'all think that tells me? Y'all won't get that many odd problems anymore? I mean, I do I'm going to be honest, I assign the odd problem so you can check your answers in the back of the book.
Yeah,
But I don't do them so you can say, heck with it, I'll just put the answer and my work's wrong, but he's just gonna look at the wrong answer. No, I look at the whole problem. So when I saw that on 5.1, I would count it wrong, and you wouldn't get any credit for it. So just kind of heads up on that. Don't try to pull anything like that. Okay. I'll get off my soapbox about that now. So our chi-squared statistic is 29.48. Remember, we said there were 9 degrees of freedom. So what would our p-value be then? That's right. So using the table, p-value with table, you get between 0.0005. Oh, this is going crazy on me. And 0.001. On the calculator, it's going to give you something like 5.37 times 10 to the negative 4 or something like that, right? Or it won't say times 10, but it'll say e negative 4. That means times 10 to the negative 4. So you would need to move your decimal to the left 4 places. So with the calculator, you would get that it was 0.0005, and then what were the next decimals? Well,
38.
you got 376. Yeah. So we'll just say 5.000538. Okay. So those are our p-values. You don't have to give me both. You can give me one or the other. Again, going back to that 12.1, I had several people say alpha is 0.01. Using our table, the p-value would be between 0.0005 and 0.001. Both are less than 0.01, so we reject. I mean, you don't have to give me the exact value with the calculator. It's good to know how to do it, so that especially for when you have multiple choice questions that ask you to find p-value or something. But you don't have to give the exact. You can use the table and say it's between these values. Okay. So based on this, let's see, do they give us an alpha for this problem? 0.01. So what would we do based on our p-value? We reject. That's right. Since p-value is less than alpha, we reject H0. Which means there is sufficient evidence to suggest that cross-standing and body arc are associated. Or you could also say are not independent. Either one of those will work. And that would make sense. I mean, that's, at least when I worked this problem, it didn't surprise me that they are associated. Typically, as you get further along in college, you may have more money to spend on stuff like that. I mean, personally, they're not my thing, but that's just me. Okay, any questions or anyone still trying to write down the conclusion? No. Okay, next example. Oh, well, let's back up. Before we get to that, let me erase this. They're asking us which cell, looking at our accounts and everything, which cell contributed most to the chi-squared statistic? Think this one contributed most? It's actually this one. He's the one. Now, granted, we didn't work everything all the way out, but what you would do is you would go through and look at each one of these decimals that you would get, or it may not be a decimal, it may be a whole number, and compare. It's the greatest one, that's right. That's the one that contributed the most to it. Okay. Next example. So we're going back to that vision correction example that we started the chapter with. So we have males and females. Those are two populations. And then we look at whether they wear contacts, glasses, or nothing to correct their vision. The first thing we do is get our marginal totals. So for contacts, what would our marginal total be? 10. For glasses, 31. For none, 38. Right, then we need to do the row marginal totals. So for female, 25. For male, and then our grand total, 79. Okay, so once we get these, we can go through and, well, hang on, let's back up. Before we do that, they tell us we need to test to see if gender and principal form of vision correction are independent. So this time they tell us we are testing for independence. There's no how do we figure it out. Well, they tell us. Test to see if they're independent. Okay, let's see. Okay, so for our assumptions for this test, we're going to assume that the samples were randomly and independently chosen. They don't tell us that. but we kind of need to do it. So one place, there's not a particular spot on your notes to write this. Maybe you want to write it at the bottom of page 13. It's up to you. But that's one thing we need to look at. And then they say all expected cell counts are at least 5. Are they? We don't know yet. Just based on how I said that? Are they? We gotta check. So, how would I calculate the expected cell count for females with contacts?
Oh, it's 10 times 3.
10 times 25, about 79. So I'm gonna write that here. 10 times 25 divided by 79. So if I calculated that, what would I get? 3.16. Oof, that's not a good way to start. First one out of the gate, boom, we're less than 5. But let's look at all the others because that'll help us kind of devise a strategy as to how we want to proceed. So for the next one, how would I calculate those marginal totals for females with glasses? 31 times 25 over 79. And what did that get us? Yep. Mm-hmm. 9.81. Nancy's getting smart over here. So what did we find on Friday for females with none? What did we find for that expected count? 12.03. I'm not going to write the equations because as Nancy already figured out, and I'm sure y'all probably now have to, we've done this same exact example Friday. So if you're wondering, wait, how did they get the counts? Look at 12.1. All the formulas are there. So for males, what were our expected counts? 6.84, 21.19, 25.97. Okay. Now, are they all greater than 5? No. We've got one that's not. So here are our two options. We can either combine male and female into one row, or we can combine contacts with glasses or contacts and none. Contacts with glasses. That makes the most sense. What would happen if we combine male and female together?
Gender is dependent on whether person needs like eye correction.
That's right. That's right. Yeah, there wouldn't be any two populations that we're comparing. And we would be back to what we did on Friday with just one population. So we have to combine columns, and then it wouldn't make sense to combine contacts with none. So contacts and glasses need to combine. Okay. So we're going to do just that. We're going to combine contacts with glasses. So how many females wear either contacts or glasses when you combine those? 14. How many males wear contacts or glasses? 27. And our column total now is 41. So we have to get new counts for this first column, but our expected counts for none stay the same. They're still going to be 12.03 and 25.97. Those stay, nothing changes. But now we've got to get the counts for the first column. So I'll do 25 times 41 divided by 79. So what would that get us? 12 point, what were we saying? 96. Okay. And that's the rounded answer. Yeah. And then we have to get our expected counts for males. $54 times 41 divided by 49. You're right, yes. It is. So what would that expected count be? 28.03. Okay, my computer's going a little crazy on me. So what would our hypotheses be? We kind of skipped right over that. We went straight to expected counts. So what would our hypotheses be?
Non-systems, categories, or independent?
That's right. Gender and vision correction are independent, which means the alternative is that they are not independent. For a significance level, we haven't chosen one, so we're going to look at the practical significance level. Meaning, we're mainly going to focus at 0.05. Focus on 0.05. As we'll see, though, even 0.05 is not going to matter.
More studies coming out saying that the default level is 3.01.
Yes, there are studies coming out saying that default, yes. Yeah, that's actually been a debate for the past like 5 years at least, that it should be 0.01, and the reason is people are saying, oh, our p-value is 0.04999999. It's significant. And you look at their data and you're like, so this is looking suspicious. What points did you take out to make that happen? Oh, take out points? I didn't take any points out. Really? You don't think it's funny that you're running around waving a p-value of 0.04999999? I mean, so now they're saying, okay, you know what? We're going to say 0.01 is statistically significant because that's a little bit harder to achieve than 0.05. And then plus that has implications in the medical field too. They can't just rush off and say, yes, our results are statistically significant. You should approve this drug. You should approve this treatment. See, they're statistically significant. It's going to be harder for them to push that through now. Okay, so we've got our hypotheses. Our test statistic is the same that we've been using. So let's calculate it. The only thing left here is to calculate and get our conclusion. Before we do that, though, let's talk about degrees of freedom for our new table. So for degrees of freedom, we have 2 rows, so we're going to say 2 minus 1, and 2 columns, times 2 minus 1. Now, how many degrees of freedom do we really have? 1. Degrees of freedom is equal to 1. Okay, now for the test statistic. How would I set the first one up? Yep. Right, then we have the next one. Uh-huh. Yep. Yeah, I'm not going to just write out all 4 of them because, yeah, there's only 4. We can write 4 of them out. Now, hopefully, when you're writing these out and you're looking at their differences, you can kind of get an idea of what to expect when you calculate. Okay, I mean, I'm looking at these and I'm thinking, yeah, these aren't big at all. I do not expect my value to be very big. That's cool. Cool. Wrong way. Okay, so there's all 4 of them. Now let's get each one individually to 4 decimal places. So for the first one, what would that one be to 4 decimal places? Zero, 8, 1, 8. Okay. What about the next one? 0, 8, 8, 2. And the next one? 0, 3, 7, 8. And the last one. That's right. And if I add all these up, what would I get for my squared test statistic? Point 2487. Okay, there's our test statistic. What's our next step? P-value. So if we use our table, what would the table tell us? Remember, 1 degree of freedom. It's going to be greater than 0.25. That's all the table will tell us. If we use the calculator, we would get something that's much greater than 0.25.
It's 0.618.
0.618. I think it's 0.6188 in 4 decimal places. Not really?
I got like 6.799.
So, what you get? 6.1. Oh, I see. You got 6.1799. Okay, so that would be 0.6180. There we go. Yeah. Okay, so for any reasonable p-value, what can we say? Let's say we used a 0.1 as our alpha. What would we do? We fail to reject. Yeah, p-value is huge, so no matter what a reasonable p-value or reasonable alpha would be, we would fail to reject. That's what we're going to say. Since the p-value is, and I'm sorry if you're watching what I'm writing, there's a lag for some reason. Since the p-value is greater than any reasonable alpha, we fail to reject. H not. Then we can say there is not sufficient evidence to conclude that gender and vision correction are, yeah, you can say dependent or you can say are associated. Okay, come on. Come on. I guess the A and the O are not going to show up. Oh, yeah. Okay, and then if you look at the last page, you'll notice the Minitab output pretty much matches. Not exactly, but it's pretty close to matching what we have. So it gives you the chi-square down here, right? 0.246, and we got something pretty darn close to that. And then the p-value, 0.620. Again, we got something pretty close to that. So, we did it right. Okay, we are we're done. Chapter 12 is in the books. So all that separates y'all from the end of this semester is chapter 13 now. And the chapter 12 test.
Okay, well, this is